I'm very, very happy to have this opportunity to tell you something about the research that I have devoted my entire working life to. I work on quantum gravity, which is not a theory. It's not a theory in physics yet. It's the name that we give to a problem. And the problem is that our best theory of gravity, general relativity, and our best theory of matter, quantum field theory, are incompatible with each other as they currently stand. We call the theory that will unite them and reconcile them quantum gravity, but that's really just a shorthand for a unified framework for all of physics. So reconciling quantum theory and gravity is famously difficult, but each actually throws light on the other, and the way in which they intertwine and connect with each other is something which supports a particular vision of the unification that I believe will come in the future. And that is what I'm going to tell you about today. So I'm going to start by telling you about quantum mechanics. And I'll start by telling you about a particular experiment, the iconic experiment in quantum mechanics, which is the double-slit experiment. The particle physicist Richard Feynman called the double-slit experiment the heart of quantum mechanics. And I don't disagree with that. So what is this experiment? Well, the experiment consists of a source of particles. Let's say that they're electrons. So this is a little gun that fires electrons at a metal plate. And if the metal plate was solid, then the electrons would just be absorbed by the metal plate and not make it through. But in the metal plate, we make two holes, two slits. That's why we call it the double slit experiment. Two slits. And electrons can now get through the plate and travel over here to where there is a backstop, a glass screen. And if an electron makes it through the metal plate and hits the glass screen, then it causes a little flash, a scintillation, a little flash of light. And we can tune the electron gun so that it's very, very weak, and it releases the electrons one at a time. So the electron gun fires a single electron, it makes its way through the experiment and causes a little flash on the screen. And over time, the flashes on the screen will build up, and we can record where each flash was on the screen and show a resulting pattern that the flashes have created. Okay. Before I show you what that pattern of flashes is, I'm going to show you a less famous experiment, which is the single-slit experiment. And that is where you cover one of the slits in the metal screen. Now you've only got one slit that the electrons can get through. The electrons are released by the gun, they travel through the slit, and they hit the screen. And the pattern of flashes that they cause on the screen, again, builds up over time. Now, with the single slit open, the pattern of flashes on the screen, the pattern of scintillations that builds up over time, one by one, so each flash causes one of these spots, is like this. It's kind of pretty uniform over a patch of the glass screen. Okay, and you can then open the second slit. Now we've got our two slits again. Now the electrons can go through this slit or that one. So both slits are open. And again, we record the pattern of flashes that the electrons make on the screen. And the pattern of flashes that they make on the screen is now this. Now, what has happened here is that from this pattern, which the electrons make if they can only go through one slit, and in particular, there's no region on the screen that the electrons can't get to. Suddenly, with both slits open, there are now regions on the screen where the electrons cannot go. So there are patches, these stripes on the screen, where no electrons ever hit the electron flashes bunch up in these stripes, and they're completely absent from these places here. So this, if we think about that for a minute, that means that with one slit open, one way the electrons can go, the electrons can actually reach this part of the screen. If you open the other slit, and now there are two paths, two possible paths that the electrons can take. They suddenly cannot reach that point on the screen anymore. Now, that is stand up, sit down, fall over, amazing. And if you're not astonished and disturbed by it, even if you've seen it before, if you're not still astonished and disturbed by it, then I just haven't explained it properly. So what is going on? And of course, we all know that, and that's the right question, and if you are asking yourself that question, that means you're a physicist at heart. Because physics is all about trying to work out what the bleep is going on. Now, in order to pursue that question and to try to figure out what is going on in that experiment, I'm going to take you now on what will seem to you like something of a detour. And it's a detour through the physics of gravity. So bear with me, right? We're going to leave quantum mechanics for a minute now. Now, our best theory of gravity is general relativity. And it teaches us that gravitational phenomena are manifestations of the curvature of a fabric called space-time. Space-time is the arena for everything that happens in the universe. But it's more than just an arena. It's more than just the stage on which everything that happens, happens. It itself is a participant in reality's grand play. It has its own lines, it has its own plot. It participates actively in the dynamics of the universe. So it's stage and actor. And here is a picture of a piece of space-time. Our space-time is, as far as we know, four-dimensional. That means to locate a point in space-time, we have to know four numbers, four coordinates to locate it, 3 to tell where it is in space and 1 to tell where it is in time. I can't draw 4 dimensions, and I've never met anyone who can. So the best we can do is to draw a picture of a 3-dimensional space-time. So I've reduced the number of spatial dimensions down to 2. This is a picture of a chunk of a 3-dimensional space-time. And I've drawn it sort of curvy like that to hint to you that this space-time is supposed to be bent and warped and curved. These slices that I've drawn here are just to guide your mind. I'm going to take them away in a minute because there's nothing physical about them. They're just meant to suggest to you that we have 2-dimensional space stacked up in time as time passes. And for all relativists, people who study general relativity, the past is always at the bottom of the page and the future is always at the top. So for relativists, do it with the future pointing upwards. Okay, what does a point in this space-time correspond to? Well, it corresponds to something like that. That's a click of my fingers at a point in space at a moment of time. Like that. That's a point in space-time. And here is a world line in space-time. And you and I and every object in the universe, every star, every galaxy traces out a world line in space-time like this. So this could be, for example, this could be I get up in the morning, this could be I go to bed at night, and this is my trajectory through space-time in between those two events. Here's another world line in space-time. This is the world line of a photon that is created in a light bulb at some event. It travels through space-time and is absorbed by my retina at this event here, where it intersects with my world line. Here is your world line. This is you catching the bus, traveling through space-time, meeting me here right now, and then going off later, and then going to the pub. So in space-time, we all trace out these trajectories, these world lines, and the ones I've drawn here on the diagram are only a tiny representative of, obviously, the complicated dynamics of all existing things within space-time. Now I'm going to take away those lines to guide your eye. This is the picture of the physical world that general relativity teaches us. The entire history of the universe, from the beginning, if it had a beginning, to the end, if it has an end, is laid out once and for all in this timeless way. And that is what corresponds to the physical world in general relativity. And in this space-time picture, certain things which at first seem rather paradoxical, certain things that you learn about when you're studying relativity for the first time, and you learn about these certain things, you find them peculiar and strange, are perfectly understandable and appear normal and indeed sensible when you have a space-time picture. So for example, people often learn about what is known as the twin paradox, where a pair of twins, the same age, decide that they're going to do different things. One twin goes on a spaceship very far away, very fast, and then returns as far to Earth. And as far as the twin who stayed at home on Earth is concerned, a long, long, long time has passed. So the twin on Earth has aged an enormous amount, gotten very old. But the twin who's gone on the spaceship hasn't aged hardly at all, maybe by just a couple of seconds, if the spaceship is fast enough and the spaceship has gone far enough. So that seems weird. That's just completely contrary to our everyday experience. When you say goodbye to your friend in the morning and you go off to work and then you come back to your flat at night, you don't expect that they're younger than you, that they've aged less than you have. However, if we think about things in a space-time way, then in space-time, the twin that stays at home traces out a trajectory through space-time. The twin that goes on the journey in the spaceship traces out a trajectory in space-time. And there's no reason at all, a priori, why the time measured by the watch for the twin that stays at home should be the same as the time measured by the clock, the watch carried by the twin on the spaceship. No reason at all. Why should they be the same? And indeed, in this space-time picture, clocks, watches, and indeed our biological processes, everything that marches out time, those processes they're odometers for time, just as the odometer in your car is the odometer for distance traveled in space. You go on a different trajectory through space-time, then your odometer for time will measure a different amount of time. So the physical world, according to general relativity, and remember, general relativity is the best science that we have, is a space-time. It's where we live. So welcome. Okay, what does this have to do with quantum mechanics? Well, early in the development of quantum mechanics, in around 1932-33, Dirac pointed out that in trying to understand what quantum mechanics is and its relationship with classical physics, there's actually a choice. We have a choice. And the choice rests on two ways of thinking about classical physics. And the two ways are based on the Hamiltonian and the Lagrangian. Doesn't matter if you don't know what those are. But essentially, in a Hamiltonian picture for classical physics, you need a time slicing of space-time. So those colored slices of space-time that I took away at the end and said were not physical, you need to put those back in order to have a Hamiltonian framework for classical physics. in the Lagrangian framework, you don't need the slices. You can talk about classical physics in a space-time framework that doesn't require any slicing of your space-time into spatial slices. Dirac called the Hamiltonian essentially non-relativistic. It's just not at one with the picture of space-time as a whole entire entity that relativity teaches us, whereas Lagrangian is relativistic. And that has consequences in trying to develop quantum mechanics from classical physics. The Hamiltonian form of classical physics leads to the wave function. And for any of you who've just done second year undergraduate physics, you'll have learnt about the wave function in your course on quantum mechanics. It comes from the Hamiltonian view, the Hamiltonian framework formulation of classical physics. Their space-time is nowhere to be seen. You have time, the wave function depends on time, and time is that label of those slices in space-time. But space-time itself is nowhere to be seen. And famously, the quantum mechanics that's built on the Hamiltonian and built on the wave function simply declines to say what is going on. So if, as physicists, our job is to figure out what is going on, then this route to thinking about quantum mechanics simply declines to give an answer to that question. The alternative, the Lagrangian formulation of classical physics, is relativistic, and Dirac showed that it leads to something called the path integral, and I'm going to tell you what the path integral is in a minute. The Lagrangian formulation of classical physics and the path integral formulation of quantum mechanics are both rooted in space-time. In these frameworks, the physics takes place in space-time. But does the path integral approach to quantum mechanics tell us what is really going on? I've claimed that the Hamiltonian approach and the wave function simply declares it to be an unanswerable question. It says not to speak about that. But does the path integral do any better? So, the fork in the road is a choice, and when in doubt, go for unity. So when you have a choice, choose the one that's most unifying. And to me, it's clear that in this case, the choice is to choose the Lagrangian. It's relativistic. It moves along the direction of unifying gravity, in which the physical world has a space-time character with quantum mechanics. So we choose the Lagrangian. We go the path integral route with, famously, Feynman, who developed the path integral further, and with two researchers on quantum gravity, Jim Hartle and Raphael Sorkin, who have both argued strongly that the path integral approach of quantum mechanics should be adopted in thinking about quantum gravity. Okay, so I'm going to tell you what the path integral is. But first, I'm going to tell you about a classical system, the simplest possible classical system that quantum mechanics is really rather like. And this simplest possible classical system is called a random walk. Sometimes it's called the drunkard's walk. Some parents might call it the toddler's walk. So, and it's very simple. The walker is walking in one dimension, just along a line. And they can only be at discrete points along the line, which I've labeled by these integers. When the walker is at a particular position, let's say we start them off at the origin, then they can step to the left or the right in one time step, but you don't know which one. It's random. So that's pretty much like a toddler who's learning to walk moves. You don't know which way they're going to lurch. It'll be one way or another way. So it's random which direction they go in, and that takes place at every time step. So here's an example of a walker. I hope you can see this. The pink doesn't really show up too well, but So after one time step, the walker has stepped to the right, say, and then again to the right, 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 left, left, right, left. Okay, and they end up at this position here, at position 2 after 8 time steps. Okay, and that is a history. It's a full description of what the walker has done, starting off at position 0, ending up at position 2, and taking 8 time steps to get there. It's a history, or we could call it also a path. Here's another one. And you can see there will be many possible paths. And which one the walker will take, you don't know at the beginning. It's random. It's a random process. The walker will take one of these paths. Which one it is, you don't know. And if we ask the question, how likely is it that the walker will end up here after 8 time steps, then the more ways there are for the walker to get there, the more likely it will be. So the more ways something can happen, such as ending up at this point here, the more likely it is. Okay. Quantum mechanics in a non-relativistic space-time, again, for a particle moving on a single line in one dimension, and again, I've simplified the problem just by giving the particle only discrete positions that it can be in, and discretizing time as well. Quantum mechanics, in some way, is almost identical to this picture of the random walker. The particle, say the electron, starts at a particular position at a particular time, and then there are a number of possible paths or histories for the electron to take through space-time to reach a particular event, which is ending up at the position 2 at the time 8. And all those histories are potential paths or histories, that the paths through space-time that the electron can take. However, it is now no longer true that the more ways that something can happen, the more likely it is. This is simply false. And why is that? So this is path integral quantum physics in one slide. In quantum physics, every path or history for the system, in this case just this particle moving on this discrete lattice, every history h has an amplitude. That's a complex number. It depends on the path, a of h. And in quantum mechanics, it's equal to e to the is of h. And s of h is the action for that path. It's a real number. This is a complex number. And the measure of how likely an event is, an event like arriving at that position at that time, is this sum. You take e to the is of h, that amplitude for every possible way that the particle can go to get to that event, and you add up all of those amplitudes for all of the histories, all those complex numbers. You take its modulus and you square it. This is the path integral. It doesn't look like an integral, it's a sum. But if we were to take the continuum limit of that discretized picture, this discrete sum would turn into an integral. That's why, so it's an integral or sum over paths. That's why it's called the path integral. Now, why you do this, why you add up these amplitudes, take its modulus and square it, nobody knows. How do we know that it's true? How do we know this is the case? How do we know that this is the measure of how likely an event is? Through experiment. Experiment drives us to this unlikely looking thing. If one were designing a world, this is not the first thing that would come to mind in designing it. This is the way it is through experiment, including experiments like the double slit experiment. Now you can see that if two histories have non-zero amplitudes, but one is minus the other one, if you add those two amplitudes together, they can cancel to give 0. So non-zero amplitudes can cancel to give a 0 likelihood. Alternative histories can interfere with each other. This is the famous quantum interference. And it's the reason that the electrons can no longer reach points on the screen that they could reach when they only had one path. When they had one path only to get there, the amplitude was non-zero, and when you square it, you get a non-zero likelihood. But when there are two paths for it to go, to two possible histories for it to reach that event, those amplitudes can actually cancel with each other, and you can get zero. Okay. So this is all very suggestive, but does it really tell us what is going on? After all, we know what a random walker does. A random walker takes one of those random paths. The toddler will actually toddle one particular random walk. So does a quantum particle do the same thing? Does it take one of these paths? Well, it seems not. And here is a demonstration that we cannot maintain the same view of the physical world in quantum mechanics as we did for the random walker. Okay? And in fact, you have to go to a triple slit experiment to see this. Okay, so this is a bird's eye view of a triple slit experiment. There's again a metal plate. This time it has 3 slits in it. So we're looking down on the metal plate. These are the 3 holes. And here's the backstop. Here's the glass screen. Here's the source of particles. And now, and this is the point where the particle is going to end up. Now there are 3 different ways that the particle can go. It can go through one slit, or it can go through that one, or it can go through that one. So 3 histories, 3 possible histories. And we can arrange the experiment, adjust the distances between the slits and the distance to the screen in such a way that the amplitude for this blue history is -1, the amplitude for the red history in the middle is +1, and the amplitude for the green history on the outside is -1. Now, the amplitudes for these 2 histories, the blue and the red, add up to 0. That means that the particle cannot travel along the blue history because the amplitude of these 2 together cancels out and gives you a 0 likelihood for the particle to go along the blue or the red history. And it can't go along the green or the red history either because these amplitudes also cancel out. So it can't go on the blue history, it can't go along the red one, and it can't go along the green one. So it can't go along any single one of these histories. Okay. I can't give you an answer to the question of what is going on. If I were able to give you the definitive answer, then I would be claiming that I had solved the age-old measurement problem and all the struggles over the interpretation of quantum mechanics would be over. So I can't give you an answer. However, we have a proposal for an answer whose implications we are still working out. So this is a proposal under investigation. The proposal is that in a quantum theory, the physical world corresponds not to a single history, as it does for the random walker, but to a set of histories. And in this case, in this particular triple slit experiment, the set of histories would be the blue one and the green one. So the physical world in this triple slit experiment would, if this proposal pans out and works eventually, would be the blue and the green history. That is what would correspond to physical reality in this setup. Okay. So I've argued that relativity in the way that it manifests itself as a space-time character for the physical world impacts on our understanding of quantum mechanics. So what about the converse? What about the other way around? Does our understanding of quantum mechanics, does quantum theory impact on our understanding of gravitational physics? Well, the epitome of gravity, the epitome of general relativity is a black hole. A black hole is an object that you cannot understand without general relativity. Black holes are the simplest and most elegant macroscopic objects in the universe. They are formed when compact objects such as stars and galaxies undergo gravitational collapse. They're regions of space-time from which nothing, not even light, can escape, and they're characterized by an event horizon. The horizon is a surface in space-time which divides the interior of the black hole, from which nothing can escape, from the rest of the universe. The event horizon is a causal horizon. Nothing that's inside the black hole can influence, can causally affect anything that is outside the horizon. And black holes obey the laws of thermodynamics if quantum theory is taken into account. Now, this is a nice story. It's something that would take another lecture to tell you about. And if you want to hear another lecture, then you can look for me on YouTube and and hear my lecture on black holes and thermodynamics. So if we ignore quantum theory, then black holes can violate the second law of thermodynamics, which is a bad thing. You don't want to violate the second law of thermodynamics. Many people consider the second law of thermodynamics to be the premier law amongst all laws. And if you violate it, then your theory is definitely a bad one. So the reason that without quantum theory you can violate the second law is that without quantum theory, you can take a black hole, and you can take some system which has a lot of entropy, and you take that system with a lot of entropy and you just throw it into the black hole, and you got rid of the entropy, you lowered the entropy. So the second law of thermodynamics says that for an isolated system, the entropy can never decrease. So, but you just decreased it, you just threw this entropy into the black hole and got rid of it. So that seems a little hokey and a bit of a cheat, but it's surprisingly fruitful to, it's less of a cheat than it seems. You can actually apparently violate the second law if you don't take quantum theory into account. However, if you do take quantum theory into account, then the work of Stephen Hawking and Jacob Bekenstein shows that black holes are actually thermodynamic systems. They have a temperature and they have an entropy. And when you and that means that you can save the second law, because when you throw entropy into a black hole, the black hole gets bigger and its own entropy increases. Okay. So black holes they obey the laws of thermodynamics. Now, in the development of thermodynamics, the understanding of that physics, the understanding of why the laws of thermodynamics are true, was advanced when people fully took on board the atomic nature of matter. So the people understood all the concepts that go into the laws of thermodynamics, and they based that understanding on the atomic nature of matter. So, for example, heat. When an object is hot, it's not because of any new substance, like a new fluid, like some kind of heat fluid that must flow into an object and out of it when you heat it up and cool it down. Heat is nothing more than the disordered motion of the atoms and molecules that make up an object. So heat has a mechanical explanation in terms of the internal microscopic constituents of an object. Temperature, similarly, can be understood in microscopic terms, and so also can entropy. So because black holes satisfy the laws of thermodynamics, that raises immediately the question, of what the microscopic physics is that explains this black hole thermodynamics. And an answer is suggested by the form that the entropy of a black hole takes. So I've used the symbol S for entropy. The entropy of a black hole is the area A of its event horizon divided by 4LP squared. So what is that? That's the area over 4 in units of LP. And what is LP? LP is the square root of G, Newton's gravitational constant, and h bar. And this is called the Planck length. It's a very, very, very small length. It's about 10 to the minus 33 centimeters. So if you take the horizon of a black hole and measure its area, and you count how many Planckian pixels, how many Planck-sized pixels there are that can tile that horizon area, that gives you the entropy. So the entropy is roughly the number of Planck-sized pixels on the horizon. Now I've kind of exaggerated this black hole horizon here as a sphere, and I've drawn these pixels on it. But a horizon, a black hole horizon, is nothing that you could recognize like that. A black hole horizon is a surface in empty space-time. And in fact, you and I and everyone in this lecture theatre and everyone on the planet, in fact the whole planet Earth, in fact the whole solar system, we could all be falling across the horizon of a very large black hole at the moment, and we wouldn't know it. There's no local signal, there's no local signature of a black hole horizon that we would notice if we are passing across the horizon of a very large black hole. There's no shock wave, there's nothing that you could point to and say, yes, now we're falling across the horizon of a black hole. We just wouldn't know it, because a black hole horizon is just a surface in empty space-time. So the value of the black hole entropy suggests that a black hole horizon is comprised of a number of Planck-sized molecules, just as the entropy of a gas at high temperature is roughly just the number of molecules of that gas. So this suggests that the black hole horizon is made of Planck-sized space-time molecules. But if the horizon is just some surface in empty space-time, it suggests that space-time itself is granular or atomic at these Planckian scales. Okay, so this dichotomy between continuity of existing things and atomicity or granularity is something which plays itself out in physics and has done since the beginning of science. And I've already argued that the value of the black hole entropy suggests that space-time is granular and not continuous. And there's at least one other indication that that will be a fruitful direction, a fruitful hypothesis to make. And to explain what that is, I need to take you back to our picture of space-time. So here's our picture of a chunk of a three-dimensional space-time. And here's an event in that space-time. Now, space-time has a certain structure, which I didn't show you before in the picture. And that structure is its causal structure. And by that I mean the information about which events in space-time, events like that, can causally influence and change which other events. So anything that I do right here and now, there are some other events elsewhere in the universe that cannot be influenced by anything that I do here and now. Basically, they are events which are very far away, And to get to them, one would have to travel faster than the speed of light, which we know is not possible. So since nothing can travel faster than light, anything that's further away than light would be able to reach cannot be influenced by me. So roughly speaking, things that are happening right now on Alpha Centauri cannot be influenced by me because it takes time for light to travel from me to Alpha Centauri. So if I'm here now, and that's me now, that's my click of my fingers, then that's an event way over in Alpha Centauri that I can't influence because it would take light it would take a signal that would have to travel faster than light to get there. So from me here and now, I can draw the world lines of all the light rays that I could send out from me. And those light rays emanate from me, and they trace out the surface of this cone. So every line along the surface of this cone going out like this from here, that's the trajectory, a world line of a photon, of a light ray. And anything that's out here, I can't influence. I can't causally influence. But anything that's inside my light cone, as an event like that, I can causally influence. I can send a signal, I can send a letter to an event like that. And this is the world line of some signal that I send out from me to causally influence this event here. And I just chose that point in space-time arbitrarily. Every point in space-time has a future light cone like this, which marks out the regions of space-time that event can causally influence, everything inside and on the cone, and the events in space-time that cannot be causally influenced by that event. That's all the part of space-time that's outside that cone. And all together, all of that information is called the causal structure of space-time. It's all the information about which events can causally influence which other events. Okay, so here's our dichotomy. Is space-time continuous, or is it atomic? So I've already given some evidence for space-time being atomic in the value of the black hole entropy. So if space-time is continuous, then it turns out that this causal structure, all those light cones everywhere in space-time, all the information about which events can causally influence which other events, it gives you almost all the information about the geometry. So you can recover all the information about how the space-time is bent, warped, how it ripples. All of that information almost is encoded in this causal structure, in the structure of these light cones. If space-time is atomic, however, the causal structure gives you all the information about the geometry, all the information about how it bends, warps, and ripples. And what the atomic structure has that what the atomic spacetime has that the continuous spacetime doesn't have is number. So the information that is missing from the continuous spacetime is actually present in the atomic spacetime because you can count. So there's metrical information encoded in just the sheer number of atomic constituents of the spacetime that is missing from the continuous spacetime. In continuous spacetime, the number of points in a particular spacetime region is infinite. There are infinitely many points in any spacetime region. But in atomic spacetime, that's not the case. The number of individual atomic constituents in a particular region gives you the volume of that space-time region. So again, when in doubt, go for unity. In an atomic space-time atomicity unifies causal structure with geometry. And because geometry and curvature of space-time is gravity, it unifies causal structure with gravity. in an atomic space-time, gravity, the phenomenon of gravity, is nothing more than a manifestation of all the causal relations between all the events that happen. So we go for unity, choose atomic space-time, for this reason as well as the black hole entropy. And this gives rise to a particular and precise proposal for the microstructure of space-time. It's called a causal set, and I've just given a very tiny indication of what a causal set is like. If this conjecture pans out, if it's true, then the causal set that is our space-time, our universe, would have 10 to the 240 space-time atoms in it. So here's a causal set with 5 atoms in it, so this is nowhere near giving you a realistic picture of what the causal set that could underlie our universe is like. But what it is a set of elements. These are these black blobs. I'm sorry it doesn't show up too well, but there are 5 black blobs here, 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 and here. So those represent the space-time atoms, the grains of space-time, and they are bound together. They make a space-time via their causal relations, and the causal relations are just depicted here as these arrows. The arrows are meant to have no length. There's no sense in which this arrow is in any way longer than that one, even though I've drawn it that way. This is just, all this is information that this space-time atom is in the causal past of this space-time atom here. So this space-time atom can influence this one. And this space-time atom can influence that one, this one can influence that one, etc. But this one over here cannot influence this one over here because there's no pathway of arrows between these two. So these are causally unrelated atoms of space-time. Now this proposal for a microscopic substructure for space-time was made independently by 't Hooft and by Meerheim, and jointly by Bombelli, Lee, Meyer, and Sorkin, and has been championed by Raphael Sorkin since then. Okay, so let me bring all the threads that I have traced out together, finally, into a vision for a unification of gravity and quantum theory. So quantum mechanics is expressed as a path, quantum mechanics of a single particle is expressed as a path integral, a sum over all the possible histories that that particle can take. Quantum gravity, then, if we are following a path integral framework for a quantum theory, quantum gravity will be also expressed as a path integral, a sum over histories, but those histories themselves will be whole space-times. And those space-times will be quantized in the sense of comprising discrete units, discrete space-time atoms, which are linked together by a relation of causality. So whether or not this particular and specific vision will turn out to have any portion of the truth in it, that's for the future to say. But something I have complete confidence in is the unity of physics itself. So in the future, we will know the truth about quantum gravity. And in that sense, space-time and the quantum will be united by history. And before I end my lecture, I have to say a few thank yous. So no career in physics would be possible without the support and inspiration of many people. And for me, the following people have been incredibly influential on me, inspirational to me and have supported me at crucial stages in my career. I'm reading a biography of Eddie Merckx, actually, the cyclist. And Eddie Merckx said that to have a passion and to be able to turn that passion into a profession is the most beautiful thing that can happen to anyone. So for me, I think my children are the most beautiful thing that have happened to me. But still, that sentiment is very, I feel very warm towards that sentiment, and I do indeed feel incredibly lucky to have been able to pursue my passion as my career. I couldn't have done it without Jerome Gauntlet, Jim Hartle, Stephen Hawking, Chris Hull, Chris Isham, Rocky Kolb, John Schwartz, and Raphael Sorkin. So thank you. I'd also like to thank the Theoretical Physics group for providing pretty much the best possible environment to pursue my work. We are united by a common goal, common drive to combine gravitational and quantum physics. So thank you to the group. You make this a great place to work for me. And also thank you to all my collaborators and students. It's been a pleasure. And finally, thank you to all of you for listening.